believe I am recording my screen now.
Okay, great. Well, we're talking about models of the atom, and this is part one. So as we work through it, we start off taking a look at some, actually, to a lot of, to a high degree, this is almost like a history of science class too, as we start to finally get into 20th century topics. Earlier this semester, I showed you a cathode ray tube-based oscilloscope, and we saw how the glowing pattern on the screen of the oscilloscope could be affected by a magnet placed nearby. And so the word cathode, of course, is supposed to represent a source of negative charges, and anode being without negative was supposed to be positive. So cathode rays, it was observed that you could generate cathode rays by taking a piece of metal and then heating it up. And by placing it in a very low, almost vacuum, that you could manipulate these cathode rays. So in this case, we have a cathode and anode, and then the electrons would accelerate because of the potential difference. But we know these to be electrons now. And this is actually the way the oscilloscope works. I had mentioned this before. Electrons are swept in rows. So what will happen is that the oscilloscope will paint one row and then move up a little bit, paint the next row, and so on, and keep doing that, but do it incredibly fast. But the key is that the velocity of the electron needs to be controlled in two axes. So this diagram shows that control of the velocity of the electrons can be done both with an electric field. These two plates would control the vertical deflection of the velocity. And then these two coils, because they set up a magnetic field, would affect the other component of the velocity of the electrons. Blackbody radiation is another piece of evidence about what's happening inside the molecule. And blackbody radiation essentially is really any glowing object. And black body means that we sort of draw a sphere around whatever this glowing object is. And essentially black body means a perfect emitter. And as you take a look at these three graphs, what they're trying to show is that the peak wavelength corresponds to temperature. So this is actually one of the very first pieces of evidence that the energy transmitted by light has something to do with the wavelength. So we can see that hotter sources glow in different colors, and they actually glow in colors that have a shorter wavelength. So this is a lab that we didn't get a chance to do, but I'll describe what it looks like. So this is a voltage versus current. And of course, we know if we had a resistor, we'd get a straight line out of this where the slope is the resistance. But in this case, what we have done is we've showed how much voltage it takes to get current to flow through 5 different kinds of LEDs. So the black line is infrared. Then we have 3 visible kinds of light, so red, yellow, and green. And then we have ultraviolet way up here. So again, if we trace this back, the threshold voltage at which an LED starts producing light depends on the wavelength. And also after that, it's linear. So if we know exactly what the wavelength is for each of these LEDs, and we know what the threshold voltage is for all these LEDs, then we could potentially see if there's a correspondence. And there definitely is. So here's the conduction threshold, the LED wavelength, and the LED frequency. Then over here, we have this sort of conduction threshold or activation voltage plotted to the frequency of light in hertz. And it's pretty linear. So that's interesting. So there's a direct correspondence between the frequency of light and the energy that the light carries. This relationship between frequency and energy became the original quantum hypothesis, so that the energy carried by a photon is equal to Planck's constant times the frequency. Now, Planck's constant is a very, very small number, on the order of 10 to the negative 34. So this is actually a very, very small bundle of energy. And so when quantum leap is used in the vernacular. In fact, it's not really meaning the same thing, because actually, if someone says, well, that was a quantum leap in understanding, that means the very smallest possible increase in understanding. So that's, a little bit of a misuse here. Now, here is Planck's constant in two different numbers, and this is worthwhile for you just to jot down, because we'll do some practice problems later on. But the key idea is that we have two. Now, so the first one is in joule seconds, which is the SI unit. But we had just started getting used to this new unit called electron volts. And that one turns out to be a lot more useful, because an electron volt is a very small unit of energy. And what we're talking about are very small units of energy. So the electron volt actually is very appropriate for us to talk about. So you'd want to have both constants down. In fact, I use this one so much that I programmed it as the value for H in my calculator. Now, this is kind of weird, because we know that something that has a frequency also has a wavelength. And if a wave has a characteristic frequency, how can it also have a discrete quantity of energy? That definitely seems like a contradiction in terms. But you can actually take a family of frequencies and add them together. So that's what's being shown down here in the lower right, is a graph that is actually adding multiple frequencies together with different amplitudes, so that we can make the center portion bigger and then the other parts less prominent. So if you keep doing this over an infinite number of frequencies that are all multiples of each other, like for instance 2, 4, 6, 8, and so on, that you can actually get the tails to almost cancel out. And we call this a localized wave packet. So it is something that has a characteristic wavelength, but it doesn't stretch out forever in all directions. It has a fixed width. And there's an exchange really between how well you can know the wavelength and how well you can know the energy, and that's actually called the uncertainty principle. We're not going to get into that too much, but if you see references to the uncertainty principle, that's where it comes from. Okay, great. Well, let's talk about the photoelectric effect. And let me set it up for you really quick by describing this, and I'm going to get out of this and talk about a simulation that I've got up and running. And we'll take a look at it a little more dynamically. Essentially the idea, and you probably have had experience with the photoelectric effect. If you've ever left something out in the sun for a long time and it gets faded, that's the photoelectric effect happening. And more importantly, the photoelectric effect is the primary reason for producing electricity with solar panels. That's, again, the photoelectric effect. It also gives you some insight about why you need so much patience with solar panels, because it's actually producing electricity one electron at a time. So, yeah, it's good for the long run, but not really great for instance, you're never going to see a car with solar panels on it driving down the road. It's just not that, in fact, that enough of a punch really to do big energy uses like that. So what we have, though, is like landing on a metal, and then we have a voltage set up here, and you can see the bias of the voltage. We have plus to the left, so that means that point C is positive and P is negative. And we know that if you heat this up, if you heat up the plate at point P, you'll start to see electrons jumping off, and then a very sensitive ammeter will be able to record that. But it's not even if you heat this up. If you just let light fall on it, you also see a flow of electrons. But it doesn't, it's very sensitive, and it also depends on the wavelength of light. So I am going to, and I'm going to do another application, and that application is right here. If you don't mind, the waiting room. Okay. Here we go. Start sharing. Yep. Unmute and just give me let me know if they can see this simulation.
Looks good, Joe.
Thank you. Thank you. All right, well, let's get into it. What's the situation? We have lights up here, and we have controls. We can control the intensity, and we can control wavelength. And then down here, we have a battery that's hooked up, and if we see electrons emitted, it can make them go faster or slower, or even push back on them based on what the battery voltage is. So let's start off with a setting that we know is going to generate electrons. So I'm going to just increase the intensity, that means turn it on, and the little blue dots moving from left to right are to represent electrons. You notice right away that some are moving faster than others. That's an important point. We're going back to that shortly. Let's see what happens if we change a couple of variables. So right now the voltage is set to 0, and I have, so let's keep an eye on that current number and see how it changes. I'm going to increase the intensity, and as I increase the intensity, the current goes up. So there is a connection between the brightness of the light and how many electrons we get. So I'm getting that down to a more modest value. Good. Now let's change the wavelength. So we'll put it on blue. Let's take a look at some values. So 0.035. And we're taking a look at the speed. Now the current, and I'm getting a few electrons, but probably too few for us to actually be able to measure. And we're going, and then we get to, now I'm in the yellow. And we know this about the electromagnetic spectrum, is that on this end, that's where the dangerous light is. Ultraviolet can cause skin cancer, but the other kind of electromagnetic radiation that's beyond the visible spectrum out here are things like X-rays, very dangerous stuff. And then the part of the spectrum that's over here, infrared, that's pretty mild. Infrared is really just heat. And then when we get out here, we have radio signals and cell phone signals and things like that. It's all pretty benign kind of radiation. But you notice the electron flow has stopped altogether. So we need to come up with a model that helps explain why only certain wavelengths cause electrons to start moving. Now let's play around with this voltage a little bit. And what I'm going to do, well, if I go positive, it's going to make them go faster because they're electrons. This is positive, it's going to make them want to go fast. But if I go in the other direction and I reverse the voltage, this is called a reverse bias. You can see that now they can't make it. So they get ejected off of this metal, but the negative voltage is pushing them right back from where they came. Now let's play along with the numbers and see what happens. If we crank up the intensity, well, we get more electrons out, but they don't go further. Yeah, so that's important connection. Intensity actually increases the number of electrons that get liberated, but it doesn't change how much energy they have. So let's go back to some mid value. Now let's turn down. This is, as my granddaughter would say, light blue. So let's go a little bit darker blue. Let's see what happens to these electrons. You notice that they're actually going further now. If I go down to ultraviolet, they go even further. Right. So once again, we know that energy is connected to wavelength. And so these electrons have more wavelength. I'm going to switch and go to a short lecture on my whiteboard. So if you have a place where you want to jot some things down, now might be a good time to grab a piece of paper or a pen or something like that. It's going to take me about 30 seconds to set up, so you have a little bit of time. How's the recording going, Dina?
I hope it's going okay.
Well, thank you very much for doing it. I really appreciate it.
Yeah, I hope I'm not messing it up.
Okay. I'll just share. I'm going to go back and I'll just check this up. Going back to I'm going to that, and I'm going to share my desktop. Yeah. Can somebody unmute and tell me if you can see my whiteboard?
No.
Can't see the whiteboard. Another way to do it. So okay. An application window. How about now?
We can see it.
Yes.
Yep. Looks good. All right, I'm going to tell you a little story here, and it's about potato farming and the photoelectric effect. Are you excited? All right, here we go. I don't know if I should have an E on that, but that's okay. All right, well, how's potato farming work in the first place? So I'm just going to do a little illustration over here. All right, here's the ground level. I don't know why the ground is purple tonight, but it is. And the way that you plant potatoes, seasonal, right? So relevant. So you get what are called seed potatoes. And seed potatoes are really ones that have lots of eyes on them, and the eyes are still there. So usually the eyes are things that you start to see growing on the potatoes when they're, tucked away in their bag or whatever. And those are actually, potential, they're buds for a new potato plant. So what you do with the seed potatoes, you cut them up and make sure there's one seed, or sometimes they're called eyes, on each chunk. And you place the chunk potato down in the bottom of a deep hole. And then each one of those eyes is going to wind up becoming a little fiber that grows up and then has leaves on it, a really neat green marker. And so then we get multiple stalks. I highly recommend this if you have a chance to grow potatoes. Joanne, are you on this? Are you growing potatoes?
I will have to.
All right. So now what happens underground? So we get these leaves out here, and that's all great. Well, what happens down here is that the seed potato needs to be at the bottom of a deep hole, because what happens is that each one of these stalks will start making baby potatoes. And the French call potatoes pomme de terre, apple of the earth, because if you grow your own potatoes, you won't believe how sweet they are. They're so good. Well, yeah, editorializing. But now, all the potatoes that wind up growing are all going to be above this seed potato. Now, why potatoes in the photoelectric effect in the first place? It's because when it's time to harvest these potatoes, you have to dig for them. Some potatoes are going to be really easy to dig for because they're close to the surface, but other ones you have to dig deeper for. And that's where the photoelectric effect comes in. So now let's draw a surface of a metal, like this. We're going to have a photon come in, and we have electrons that are in this metal. Some are close to the surface, and some are deeper down. So they're kind of like potatoes. The electrons that are deeper down are going to be harder to dig for. So now we have a photon that comes in, our localized wave packet that looks like this. Like that. So a little wave packet that's coming in at the speed of light. And the energy it brings with it is Planck's constant times the frequency, which is also equal to, if we want to solve for wavelengths, would be hc over wavelengths. Now that energy is going to go into liberating these electrons. And when an electron comes out, when it gets ejected, it's got a characteristic velocity. And that velocity translates to kinetic energy. Now remember that simulation we just took a look at, not all the electrons had the same amount of velocity, because the ones that are harder to dig out, well, that's going to require more energy. So whatever energy is left after ionizing these electrons can go into kinetic energy. But some are actually going to be too big for this photon to dig out. The ones that are on the very surface, the easiest ones to dig out, are going to have the greatest velocity. So what we can do then is imagine this. This energy is going to go into two places. It's going to go into liberating the electron, ionizing it essentially, and then it's also going into kinetic energy. So HF equals, this is the energy of the photon, becomes two things. Becomes kinetic energy plus what it costs to ionize. There. So the energy of the photon is going to be shared doing two tasks in order to make this happen. I need to ionize the electron, first of all, and then whatever's left over is going to be in the form of kinetic energy. Now, there's a minimum amount of energy needed to ionize the very top electrons. That energy is called the work function. So we can rewrite this statement one more time. HF equals KE max plus the Greek letter phi, which is the work function. Okay, let's do an application really quick. I want to see if this works. I'd like to take a look at some data points here. Can somebody unmic and tell me if you can see the simulation again?
Not yet.
Okay, good. So that's something I have to do in Zoom. Hold on. Stop sharing. Then I'll share again and choose the option and then choose simulation. Well, now.
Yes.
Cool. Let's pull some data. And in order to get some data, what I can start off by doing is I've got 381 nanometers here, so I'm just going to jot that down. And we'll do an example. So we're about 40 minutes in. And I think what I'd like to do is just do a couple of examples with you really quick. And so I'm writing down 381 nanometers. Now what I'm going to look for is, well, as you're taking a look at it and follow my mouse along, you can see that some of the electrons make it pretty far, and some of them don't make it very far at all. So the ones that don't make it very far, those are the electrons that were down deep. But the ones that make it the furthest are the ones with the most kinetic energy, so they must have been closest to the surface. So I'm going to take this battery and I'm going to let them go a little bit further and see if they make it all the way. Oh, look at that. Close. So I'm just about there, about 1 volt. Okay, and it looks like if I just decrease it by a little bit, then some electrons, I'm trying to get to the point where I start to get current. Ooh, that's probably too much. Yep. All right, how about minus 0.8? Yep, somewhere just, how about minus 0.9? All right, I don't want to spend all night trying to find the magic number here, but the one was actually pretty good. Let's see if I can just type into this field. Yeah, so at 0.9 volts, that looks pretty good. Yeah, okay, I think I found it. So negative 0.95 volts. We call this the stopping voltage. So 381 nanometers is stopped by a voltage of 0.95. So that means that that's to the maximum kinetic energy. So I'm going to stop sharing. I'm going to go back to my web. Can somebody on mic can confirm that they can see my whiteboard?
I can see it.
Great, thank you. Well, let's get into it. So this is our wavelength, and this is the stopping voltage. So this is also equal to the max kinetic energy. We saw that not all of them had the same energy, but the ones that had the most kinetic energy, they made it the furthest and got turned around right at the very edge. So let's take a look then at what the work function is. So find work function. And then hopefully you have a calculator with you, because I'm going to ask you to do an example in just a second. All right, so the energy of the photon is equal to the max kinetic energy plus the work function, and that's what we're looking for. Well, we just said that the stopping voltage is code word for the max kinetic energy. So that's 0.95 volts. And we need to do that as energy. So Ke max is going to be equal to Q times V, where Q is the charge on an electron. And so that's 1.6 times 10 to the minus 19 coulombs, and then times 0.95 volts. And that'll give me the kinetic energy in joules. But we don't have to do that, because we have this really cool unit called electron volts. So really, this is just 0.95 electron volts. Just like the way if you write kilometers, K stands for 1,000. Well, in this case, E stands for if you need joules multiplied by 1.6 times 10 to the minus 19. But we don't. So that's great. So I come over here, and I know that hc over lambda, this is the same thing as Planck's constant times the frequency, and that's equal to 0.95 electron volts plus the work function, and that's what I'm looking for. So this is what I want to find value for. And when I go back and I take a look at Planck's constant, I want to use the one that is in electron volt seconds. So this is 4.141 times 10 to the minus 15 and that's electron volt seconds, multiplied by the speed of light, which is 3 times 10 to the 8 meters per second, and then divided by the wavelength. And that's in nanometers, so we're going to have to write that out in meters, but that's pretty easy. 381 times 10 to the minus 9 meters. Okay. Equals 0.95. And I'm going to drop the units here, because that's electron volts anyway. So since each one of these three terms is energy, then it'll be electron volts for all of them. Okay, let's go ahead and see if you can do this on your calculator. Let's see how that's holding up. Let's see if I can put a little bit more light here. I don't know if that helps. I'll try and increase the contrast. That's not working. There we go. So that's a little bit better. Uh, 4.141 E negative 15, then times 3 E H divided by 381 E minus 9. Okay, so that's 3.26 electron volts. Great, so I just have to subtract 0.95, and you can see that actually the math is not bad at all. So the work function is 2.31 electron volts. And the work function for different metals is going to be different, but as long as you're working with the same metal, the work function should be the same. So let's try this. These things are just barely making it out. So what we're going to do is we're going to make a shorter wavelength, which should give us more energy to work with. So here's what I would like you to do. Given that this metal has a work function of 2.31, let's suppose we hit it with a different wavelength of light. So let's suppose we're going to do wavelength of 92 nanometers. And given that we're not going to change metals, the work function is still 2.31 electron volts. Then let's find, let's see, what are we going to be looking for? The stopping voltage. Okay, stopping voltage is kg max. So we're going to find this number. So Hc over lambda, you're going to change lambda to be 92 nanometers. And then we want to find out what this is going to be, but we know this is 2.31 electron volts. All right, let's go ahead and give this a try and see how you do. I'll give you a couple of minutes to do it up, and I'll be doing it myself. And then we'll go into the simulation and see if it works. So you can try it on your piece of paper. I'm going to work on it on a whiteboard. Actually, I need that. So you could follow along with me, or you could just turn away from the screen and see if you could do it on your own. And then I think this will be a good place to stop, because that'll give you enough to work with to do some practice problems with. going to require me to string. I can see you all really quick. You want to give me, how are we doing? Thumbs up? Meh. Thumbs down? Okay, good. So you should have enough. And let's just verify really quick. So I'm going to go back to share and choose photo electric effect. And see if I can turn it to how low can I go? Almost. Okay, look at them zip across there. I wasn't sure how far down it would go. I said 92 nanometers. We're at 100, right? So we're going to really crank this up, and it says we should go up almost up to 11. And you can see we're starting to push some back. But anyway, I think we demonstrated what the point was, so I'm going to stop sharing. And I'm going to go ahead and unmute all. And any questions?